Welcome to Oddly Real. I'm Nem Stefanovic. When we look out into the vast cosmos using our most powerful telescopes, we see a brilliant array of stars and galaxies. In fact, we don't just see the universe from its visible light, but across the electromagnetic spectrum. We can detect the presence of intergalactic gas from its radio wave emissions to powerful sources of energy emissions that emit high energy gamma radiation from supernovas, pulsars, and black holes. Yet, there's something else permeating the cosmos. It's not anything that we can see or detect, but seems to be present almost everywhere. We know something is there because there is a strong gravitational presence that causes discrepancies in how stars orbit galaxies, how galaxies move amongst each other, and what we observe in a phenomenon called gravitational lensing. Whatever this is, it doesn't appear to interact with normal matter other than through the effects of gravity. I'm of course referring to dark matter. As mysterious as this substance is, perhaps more shockingly, it's by far the most dominant form of matter in the universe. There is 5 times more dark matter in the universe than visible matter. In this episode, we'll discuss what we know and what we don't know about dark matter. Additionally, we'll talk about what evidence exists to support the idea that dark matter is indeed real and how it influences visible matter in the universe. Would you be surprised to hear that only 5% of the entire universe is made from atoms of ordinary matter? Incredibly, the other 95% of the universe consists of dark matter and dark energy. We will focus on dark matter for our discussion here, and even on its own, it is 5 times more abundant in our universe than visible matter. Strangely though, we don't know what it is. Whatever dark matter is, it doesn't seem to interact with most forces, like the electromagnetic force or the strong and weak forces. It only seems to interact with matter via the force of gravity. Additionally, it permeates our universe, occupying the same space where stars and galaxies are present, and even beyond. If we can't see dark matter, and it doesn't appear to interact much with normal matter, then why do we think dark matter is present, and in such large amounts? There's lots of evidence that points to the existence of dark matter throughout the cosmos. In one example, there are discrepancies in how stars orbit the outer regions of their galaxies. Stars tend to take elliptical paths and many times very close to circular paths around galaxies. There tends to be a large density of stars at the center of galaxies, with lower densities of stars as you move radially outward to the edges of the galaxy. A star that's in orbit very close to the center of the galaxy feels the force of gravity pulling on it most strongly from the stars that are behind it, towards the center. In fact, as you move out radially further away, but still within the galactic bulge at the center, orbiting stars would see even more stars behind them, and their aggregate gravitational attractive force would feel even greater. This effect changes moving far away from the galactic center into the outer regions of the galaxy. In this case, there are far fewer surrounding stars over a much greater volume to contribute anything significant to the pull of gravity. Instead, the force of gravity will start to weaken, since the most dominant source of gravity is from the galactic center, but we're much further away from it at the galactic edge and beyond. So moving outward, we'd expect the overall pull of gravity to diminish, and the stars in these regions would orbit more slowly. If the stars move too quickly in this outer region, gravity wouldn't be strong enough to hold onto them, and they would be ejected from the galaxy. We can observe the total visible amount of matter within galaxies to estimate its total mass. We can also observe the speed at which stars orbit around their galaxies. The mass estimates and the stellar orbital speeds tend to be in agreement around the galactic center and even a bit further out. However, this is not the case in the outer regions of the galaxy. Orbiting stars do not seem to slow down, but stay moving fast. In fact, they maintain their speed far out, even beyond the galactic edges. They are moving far too fast for the observable matter to hold on to them, and yet their orbits are stable. It's as if there's additional hidden dark matter surrounding the galaxy. This tends to be the case for almost every observed galaxy, and even more surprisingly, a typical galaxy is estimated to contain between 2 to 4 times more of this dark matter than the visible matter. In another example, we are also able to observe the movements of galaxies amongst other galaxies to understand how their gravitational forces influence their movements. Our own galaxy, the Milky Way, is part of a cluster of galaxies. This cluster includes our neighbor galaxy, Andromeda, which is 2.2 million light years away, the Large and Small Magellanic Clouds, and other galaxies. Andromeda is moving toward our galaxy at a speed of 100 kilometers per second. This is a very fast speed, and most of the attraction Andromeda is experiencing is coming from the force of gravity of the Milky Way itself. Yet, in order to explain this attraction, some estimates put the dark matter content of our galaxy at figures upwards of 10 times more than the visible matter within. Additionally, there are also estimates suggesting the dark matter halo surrounding the Milky Way could extend millions of light years beyond its visible edge, perhaps as much as 70 times further out than its observable radius. Furthermore, our local group of galaxies is being pulled towards a supercluster of galaxies in the constellation of Virgo, which is 60 million light years away. This supercluster contains thousands of galaxies. The Milky Way is moving towards Virgo at 600 kilometers per second. Estimates here put the dark matter content within the supercluster at 30 times the amount of observable visible matter. Even observations of other superclusters, like the Coma supercluster, which contains 1,000 galaxies bound together by gravity, has huge discrepancies in the speed of the galaxies relative to the total observed mass in the cluster. The cluster would be expected to blow apart, but it doesn't. It is estimated that there is 9 times more dark matter mass here than visible matter. Gravitational lensing is another method to observe and estimate distant masses in the universe. Large, massive bodies distort their surrounding spacetime such that passing light from behind them is deflected around the body. Light travels out in all directions. If there's a source of light directly behind another more massive object, the more distant source can look like a ring or the arc of a ring around the massive body. This is called an Einstein ring, and it's a distorted image of the more distant light source. Even volumes of space that contain large masses, like clusters of galaxies, can distort the shapes of more distant galaxies behind them. We can compare the observed ring distortion with the total visible mass of the gravitational body. Usually, there's a very large discrepancy. In general, there appears to be more mass in the universe than we can see across the entire electromagnetic spectrum. What can account for these observations, and why do we think dark matter is a likely explanation? The most obvious explanation of the discrepancies between visible matter and the motions of stars and galaxies is that we just aren't detecting large quantities of normal visible matter. If this was true, then in fact, we wouldn't be detecting the vast majority of normal matter, since we expect to have 5 times more dark matter than what we can observe as visible matter in the universe. What if there are large clouds of cool, neutral gas floating around space that we aren't observing? We're actually quite good at detecting matter across the entire electromagnetic spectrum. For example, cool, neutral hydrogen gas emits a 1,420 megahertz radio signal, which is observable by radio telescopes. Cool, interstellar gas isn't dark matter. What about larger, more massive objects that don't emit much radiation? Specifically, there could be invisible objects like black holes, brown dwarfs, or rogue interstellar planets that might be able to account for the missing mass. These types of objects are classified as massive compact halo objects, or MACHOs. In fact, experiments have been done to test this hypothesis. What happens is that a distant observable star is monitored. When a massive object passes in front of it, the star tends to brighten, due to a microgravitational lensing, which results in some of the light being bent around the passing object's body. This is distinct from the natural flickering of light from the star, since all wavelengths of the star's light brighten across the spectrum for a passing massive object. This approach has actually detected MACHOs. Unfortunately, what we see just can't account for the enormous discrepancy of missing mass that we see in the universe. So MACHOs aren't the source of dark matter. What about neutrinos? Can they account for the missing mass in the universe? Interestingly, neutrinos are prolific across the universe. These are known as ghost-like particles since they really only interact with normal matter through the weak force, but they don't interact via electromagnetic radiation. They possess a small amount of mass, but there are estimates that suggest there are 100 neutrinos per cubic centimeter left over from the Big Bang. This sounds like a good candidate. However, the physics just doesn't work out. Neutrinos have such a small mass, and they travel at close to the speed of light. We'd need a region of space large enough to contain thousands of galaxies to have enough neutrino mass to allow them to gravitationally attract together. There are also other problems too, since estimates show that it would take too long to form galaxies using this explanation. Clustering wouldn't start to happen until 2 billion years after the Big Bang, which contradicts observations that show some ancient galaxies that formed only a few 100 million years after the Big Bang. There are also suggestions that perhaps dark matter is a form of matter called a WIMP, or weakly interacting massive particle of some kind. This particle wouldn't be able to interact with the electromagnetic force. It would be very massive, ranging from the mass of a neutron to thousands of times heavier. It would be slow moving and had to be generated in sufficient amounts in the Big Bang. What that is, we don't know. But there's a long list of theoretical particles that haven't been proven to exist, which might account for it. Or perhaps dark matter is something even more exotic, something we've never thought of before. There's a whole other avenue of investigation into dark matter that suggests maybe there is no dark matter at all. And maybe the problem is with our understanding of the laws of physics. Maybe on large cosmic scales, physics is somehow different. There are actually multiple theories that have been proposed along these lines. However, there is also some interesting observable evidence that challenges this idea. For example, there have been recent discoveries in the last decade that have identified a number of galaxies that rotate exactly as predicted by the known laws of physics. In other words, there appear to be galaxies that don't have dark matter present. If there was a problem with the laws of physics, we'd expect there would be an issue everywhere for all galaxies. There's another interesting example involving the collision between two clusters of galaxies called the Bullet Cluster. These are two galaxies that collided and passed through each other. The galaxies also contained large clouds of hydrogen gas. In fact, the mass in the clouds of hydrogen gas are much larger than the mass that's within the galaxies themselves. When the clusters collided, the galaxies passed by each other, but their gas clouds interacted by merging together, heating up, and staying held in place in between the separated galaxies. We can observe the effects of gravitational lensing from each galaxy and the large cloud of gas in between. If there was dark matter in the galaxies, we'd expect that dark matter to pass through the gas in the collision and stay within the galaxies. This is exactly what we see. Despite more observable mass in the cloud of gas, there is more distortion from gravitational lensing in the galaxies where dark matter is present rather than in the cloud. So what is dark matter? We just don't know. However, there's lots of research trying many different approaches to try to detect it. This includes searching the center of our galaxy, which contains the highest density of dark matter in the galaxy, for excess neutrino emissions or unusual gamma radiation sources. There are also particle accelerator experiments that try to account for imbalances in energy or momentum, which could indicate the creation of escaping undetected dark matter. In either case, nothing has been found. In fact, dark matter should be everywhere around us, including here on Earth, with one dark matter particle present per volume of space about the size of a human fist. There are also some intriguing opportunities to search for dark matter in certain dwarf galaxies that only seem to have a few stars, yet 100 times the amount of dark matter compared to their visible matter. Ultimately, the search for dark matter continues. I hope you enjoyed this episode, and remember, oddly real, really interesting.